Thank you, Chairperson. My name is Yoshimasa Takahashi from Kansai University. Today I would like to present my study with this title. First, let me give you a background. These pictures show, with the advancement of process technology, various small structures are fabricated into devices. These pictures show quantum dots or quantum lines on a substrate. And these pictures show multi-layer circuitry in LSI devices. Because of the elastic mismatch between different materials, severe stress concentration occurs particularly at free edges. As you can see, this air gap interconnect has free edges even inside the device structure. So it is important to evaluate the fracture initiation or fracture nucleation strength of these small components. So, this is the review of the conventional fracture mechanics. This is the formula showing this asymptotic near stress of dissimilar materials. Here, sigma is the stress along the interface, and r is the distance from the interface free edge, and k the stress intensity factor, and lambda the singularity index. So theoretically, the sigma diverges to infinity when r approaches 0, which is called stress singularity. And it is well known that the fracture initiation from the interface free edge can be described by this criterion. I mean, if the fracture toughness, Kc, is attained, then the fracture initiation occurs. And the question is, if the size of the component shrinks, then the stress singularity region similarly shrinks down. So what happens if the characteristic length of this device structure attains, for example, 1 micrometer or less? Then the singularity region shrinks down to 100 nanometers or even less. So is the criterion applicable for submicron scale structures or not? So the aim of my research is partly to verify the fracture mechanics criterion at sub-micrometer scale. And actually, this theme has been eagerly done by the professors, for example, Sumigawa or Professor Hirakata, who are attending this symposium. And what I would like to do in my presentation is that I would like to extend the series of studies to include the effect of environment. I mean, I would like to confirm whether the criterion, fracture mechanics criterion, can be applied when these devices are subjected to severe environmental degradation, for example, typically hydrogen embrittlement. So, let me show you the methods of this study. First, this is the special electron microscope I used in this study. It's called RSHVM, Reaction Science High Voltage Scanning Electron Microscope. And what's new about this microscope is that we have a gas chamber environmental cell, which can be either inserted to or extracted from the column on demand. And we can make a local gas environment around the specimen. And the acceleration voltage of this electron microscope is 1 megavolt, which is very high, much higher than the conventional TEM. The reason that we use such high voltage is that if we introduce gas, electron beam would normally be scattered by the gas molecules. So that's why we use such a high voltage. And this is an example of the electron energy loss spectrum of gas. Here, the pure neon 50 pascal, and helium with a slight amount of hydrogen. And when we compare these diagrams, we can clearly see the characteristic peak of hydrogen at 13 electron volts. So if we introduce hydrogen gas, we can actually make the environment of our environment containing the highly active hydrogen. Even if the absolute pressure is 50 pascal, so it's very slow, but small. But the actual fugacity, the actual effective pressure of hydrogen is very high in this environmental cell. So next, the specimen preparation. First, we used our material with silicon and copper, and silicon wafer with copper and silicon nitride thin films. And we firstly deposited carbon deposition by focused ion beam technique, and then made some trenches around the carbon layers. And then we picked out this small block by a solid probe and moved and mounted on this block on the top section of a metal wire. Here we used gold wire. And then the block was further thin by fifth, and a cantilever shape is formed from one side. And finally, sharp wedge having a tip just at the interface of interest was introduced. And these are two types of specimens we examined. Type A has 135 degrees angles on both sides of copper and silicon nitride. I mean the 90-degree wedge opening angle. And this shape has two singularity values, which were derived by solving Bodi's characteristic equation by using these elastic constants we obtained from the 0.45 and 0.1 or so. And the plane specimen, 90-degree, 90-degree shape, we had only one singularity value. This is just an elastic analysis. And the machine we used in this experiment is shown here. It's a nano-indenture whole specimen holder, which has 3D piezoelectric tube. This can move the specimen in XYZ direction at the resolution of about 1 nanometer. And what's important is that we have a MEMS small load sensor here, which can make a very, very small load. And we move the specimen at here. We can see in the optical microscopy here. And this is the TEM. So we move this specimen with this piezo tube and move toward the tip of the diamond emitter. And then press, and then measure the fracture load. So let me show you the results. So this is an example of a video showing the in situ observation of fracture test. Could you please click on the right side of, yes. Oh, I'm sorry. Could you click again? No. But the right side? The right side doesn't move. Yeah. So maybe I think this is the problem of codec. So it's very so it will not be solved in this time. So let me show you in my laptop. Yeah. Okay. Please see this laptop.
Screen.
Yep.
Yeah. That's not playing on the screen.
No, but it doesn't move. These work together. Yeah. Okay. Let's do this. Okay. the load almost linearly increases with time, and at the peak load, then the fracture occurs along the silicon nitride and copper interface. Okay. So, what we can see from this chart is that although the vertical axis is time, it could be viewed as kind of displacement, because the other part of the specimen is very rigid compared to this cantilever portion. So if we look at this as a displacement, very linear displacement curve can be is seen here. So from here, we can say that we have not so much plasticity of copper. And so in this analysis from here, I assume that copper layer is elastic. And this is the elastic model of the FEM. We used these elastic constants and made a 3D model by Abacus, and applied the half of the critical load, because in this model we used XY symmetry condition. So we applied half of the critical load. So this is the result of stress along the interface. Here again, the abscissa is the distance from the free edge, and the ordinate is the critical stress along the interface. And the left one is the linear plot, and this is the right one is a double logarithmic. As you can see in the double logarithmic plot, elastic singularity can be shown in both stress components. Here, the white mark is a normal stress, normal to the interface, and black plots are shear stresses parallel to the interface. So the shear stress component is much lower than the normal stress components, and when comparing these number 1 and number 2 specimens, shear stresses are completely different, But the nearest normal stress show very good agreement, and they are synced to one simple relation. So we can calculate the apparent stress singularity as 0.46, which is almost the same as the theoretical value I showed previously. So from here, what we can say is that the fracture initiation from the copper silicon nitride interface edge can be characterized firstly by the normal stress singularity parameter, SIF. And so by applying this to see the environmental effect, here I show you the bar graph. This is the final picture. And the left one is for type A, and the right one is for type B. And type A has a higher singularity, and type B has a lower singularity. And what we can see is that actually the strength from the interface edge is actually reduced by the existence of hydrogen gas. This is the same for type A and type B. But what was so interesting and more, I don't know the reason right now, but the type A, the reduction is about 30%, which is very large. And for type B, the reduction is about 8%. So we have actually don't know much about why this happens for different types, but the aim of this study, the quantification of environmental degradation by the fracture mechanics was achieved. So let me close my presentation here. Thank you very much.